Hey again, everybody. This is Mike Odell from the Penn, Ohio chapter of the SCTE. We're super thrilled to have Greg Lumen from Adtran, Business Development Manager, joining us today to talk about PON. So today's video is brought to you in partnership between the Penn, Ohio chapter of the SCTE and Adtran, bringing the world together. Thanks for joining us today, Greg. How are you today?
I am very well, very excited to be here. Thanks for inviting me. Thanks for setting all this up, logistics and all the editing you're going to do shortly.
Well, hopefully we won't need too much editing, but we'll edit as necessary. So thank you for joining us today. Adtran is a leader in passive optical network technology. So we're really excited to kind of start at the beginning and talk about PON and what it is, how it works, and some of the core components that are involved in PON for our audience. So looking forward to today's conversation.
Absolutely. Absolutely. I got to get one window straightened out here. Well, there it goes. Perfect. Yeah. We want to dive in and get into some of the basic PON info. And we're going to talk about kind of some of the standards and platforms that are out there, and really the piece parts and the components that make up these PON networks. And for those of you that are new to the lingo, PON, passive optical networking, a very popular way of doing fiber to the home. And we'll get into some of the guts and why and how PON is a little bit different than what you may traditionally have thought about for doing a fiber deployment. What we'll talk about kind of applies to a lot of the systems that are out there today. We'll talk a little bit about some future standards that are emerging right now. But really, as we said, get into the basics of it and talk about what all these bits and pieces are and what it is that really makes a PON. So the passive optical network, number one, it's optical. It's all fiber based. That's a big thing. We're all delivering fiber to the home. Putting fiber in our telecom networks is all the rage right now. So this is probably the market leading approach to getting that fiber deployed to all the homes and businesses that we're working to cover. One thing to note, it's a shared optical infrastructure. That's off-putting to some, the shared nature of it. It's, not one dedicated fiber going from point A to point B. There's some splitting going on, but that's also the thing that gives it its power. I call it the magic of a splitter. Because we're able to attain some economies of scale with this network architecture that we haven't had in the past. So it drives the economics of the network into an area where we can actually afford to build them, and we can afford to do residential services that all of us as consumers, we can keep both arms and both legs to have just wonderful broadband service turned on in our home. PONs themselves massively deployed across the globe. This isn't anything that's unique to North America. It's standardized by the ITU, so that is one nice thing. Globally, that standard is very well followed, very well respected. There's been a lot of different flavors of PON over the years. And we'll get to some of these standards that you see here, the A-PON, the B-PON, GPON, XGS-PON, all of these different variants here. Think of these as the active standards. This is really governs how much bandwidth we're going to be able to push through this technology. Our first shot at PON was A-PON, that stands for ATM PON. We were able to do a grand total of 155 megabytes across that system. Needless to say, we did some kind of scientific type trials in the 90s with APON, but 155 megabits, and when it's on a shared infrastructure, it's really not a whole lot of bandwidth to distribute. So we very rapidly moved up into GPON, which will do 2.5 gigs, and today, really the variant of the day is XGS-PON, and that X stands for 10. So 10 gig PON. This is where we're at today, and then moving on to a few things in the future. So all of these standards that you hear with the vocabulary up front, that's your active piece. That's the standard going to govern that bandwidth that I talked about. But really all of them, they run over the same layer 1 or layer 0 infrastructure. We build the same kind of PON, passive optical network, and really, whether it's APON, BPON, GPON, or out to 50 gig PON, that physical infrastructure that is so important and relatively intensive to build, we can build that once and run all of these different generations across it. So these components that are up on the screen, these are splitters, or maybe they're just some fiber interfaces. If this card got dropped in a network to facilitate BPON 10 years ago, and if this equipment's still in good working order, those standards help us keep that device in place. So we can kind of set that physical plant, we can set that up, and then run these multiple generations of technology. We don't have to go through and dig up the ground every time we want to move from GPON to XGS-PON, or as we move into 50 gig PON, or the 200 gig PON. That'll be my next bullet on this slide. So the standardization of passive optical networks has really been a big blessing. So what makes a PON kind of special? What differentiates it from what we did in the past? And what we still do today. What we did in the past was a point-to-point network. Typically, if we're thinking about a service provider network, or this could be a LAN in a building is going to be built this way. Point to point, we start at point A, which is our active component, and in this example, it's an Ethernet switch. But between all of these different units, we have dedicated cabling going from point A out to point B's through Z's, if you will. So this red infrastructure here, in the case of a LAN, this is going to be copper cable. But once you get into the fiber of the home world, this becomes a fiber optic cable. When you're in a LAN, this cable is 300 meters or less. When you're in the outside plant, in the service provider world, this cable might be 30, 40 kilometers. So anything we can do to optimize our cable plant is going to save us CapEx in the long run, be easier to deploy. So that's really one of the magical things that PON brings to the table, is our passive optical network. We introduce a new component, and that's called an optical splitter. That optical splitter sits between our point A, the PON. In this case, we've got it labeled as an OLT, but let's just think about this as point A for now, out to our subscriber or our point B. So with a passive optical network, we can take one port off of our point A, bring that into a splitter. My animations are a little backward, sorry about that. But we can bring one port and one connection into a splitter, and then we get this kind of port multiplier effect out of this splitter. So now we're sharing one port on our point A out to multiple points at the end of this network. And that optical splitter and the optical fiber cable, that's what allows us to get that kind of multiplier effect. This saves a lot of capital expense back here in point A, in our head end location. Like I mentioned, this is labeled a PON OLT. OLT stands for optical line terminal. I'll show you some examples of these in a minute. But this is the start. This is your first active component in a PON network. These red lines are going to be fiber optic cable. We come off the single port in the OLT into the splitter, and then we get that multiplier effect where we're lighting up several endpoints. So that splitter itself provides it's really, I call it, it's the magical part of this technology. One fiber in, many fibers out. and you get that port multiplier effect. So you can cover a whole lot more endpoints with less resources at the start of your network. This is what has driven service providers to the PON architectures. It saves a lot of time, a lot of effort in the build outs and the capitalization and funding of these particular networks.
So that fiber could be a currently deployed fiber that was maybe dark fiber,
yep,
or spares for a traditional HFC node location, and now we can leverage that particular fiber, or even well, I was going to say wavelengths within the fiber, but at that point you do need a dedicated fiber for multiple wavelengths, right? Between your hub location and potentially your OLT, or your OLT and your fiber splitter location.
Yeah, and you bring up an interesting point. What we're doing here is, this is optical technology. DWDM is definitely part of this solution. Hasn't been leveraged a whole lot directly in the PON network itself, but we're doing DWDM concepts here. The idea that we can take this splitter and send that signal out to multiple endpoints, that's part of the DWDM solution set, if you will. And we've been doing, splitting and combining of fibers for different applications for a number of years. PON tends to get it, has standardized it and then kind of put it on steroids. So a service provider can adopt these standards and start building kind of rinse and repeat. Now with your active HFC node, I don't have a good drawing of that here, but no, that's an absolutely great application where you've got your active node out there, backhauled with multiple fibers, and maybe today there's 24 fibers out there, and you're uplinking 2 of them. You've got 22 dark fibers left over that are going back to kind of this centralized location where you can plant an OLT, and parallel to that HFC node, you could put a splitter in there and start building out a PON network on that dark fiber. Now, to your point, your connectivity out to your HFC node, you may have used some DWDM to get, multiple waves of 10 gig out to that HFC node and increase the bandwidth out there. When we build our PONs, you are going to run into those cases where I can't run 2 sets of PON on the same fiber. So if I'm doing GPON deployments, GPON port 1 on my OLT is going to connect to one fiber, GPON port 2 is going to connect another. We can't mix and match individual, say, PON ports, or GPON ports, I should say. But what we can do is, as you saw that list of technologies, APON, BPON, GPON, XGS, is we are leveraging DWDM because those services run at different wavelengths. And I'll get into this in a couple of slides, but you can simultaneously run GPON and XGS-PON across the same fiber. And that's been kind of a cost-saving methodology.
Yeah, and I find it interesting, you and I were talking earlier, Greg, about there's always been this bifurcation of architecture, and said either an operator is either an HFC provider or a fiber provider. And I think there's some really interesting opportunities where operators are going to be able to leverage their current existing fiber assets to deploy both.
Yep.
And as we've seen, a lot of, I guess, densification is a word, where our legacy analog optical node models were, once upon a time, we may use 2, 3, 4 fibers for our optical transport back and forth between a single node location. And now we may be down to a single wavelength in a single fiber to feed an optical node, so that those currently existing fiber assets can be leveraged to expand the footprint or the geography of the node with a fiber-based technology like PON to reach that, that one farmer that sits on the outer edge of the node footprint that we couldn't serve with coax before. So I think there's some interesting opportunities to start to think about the convergence of legacy HFC architecture and the introduction of PON over the same fiber plant with just a different last mile delivery.
Yep, and there are a lot of things you can do in your network that can either reinforce what you're already doing, say add more capacity to an exchange that's hybrid fiber coax fed. You could do a fiber to the prem overlay, where you're simply reinforcing what you're already doing. But I've worked with a lot of telco customers as they've transformed from twisted pair copper over to fiber. And that was kind of a unique point in time, because to do that transformation, you truly had two networks. And you have that today with hybrid fiber HFC nodes, where I'll just kind of borrow this example. If these are your subscribers out here, this is coax cable. You overlay, your first overlay to get to all fiber can be, I'm going to set a splitter next to my HFC node, and then I'm going to parallel my coax drops with fiber strands out to the home. So that you could do that in terms of, hey, I want to reinforce this area. I've got, every fifth customer is going to get fiber, that sort of thing. But that also sets you up then in the future when you want to do that mass transformation from all those coax drops over to an all fiber network. Then you've got two parallel networks, but they're built on top of each other. And it's that fiber and the DWDM capabilities that are available today that can enable you to do that, where you don't have to touch this kind of middle mile piece.
That can allow for the offloading of maybe some of your heavier traffic users from your HFC plant, to a different service group over your optical plant.
Yep.
So lots of possibilities here. Okay. Sorry to derail. Back to PON and the basic PON construction components.
Yep. And Michael, correct me if I'm wrong, but I kind of think that this basic PON construction drawing is not all that different than your HFC drawings that you're used to seeing.
It's really not. If you think about it, the OLT is the node. And then you typically leave the node with a piece of coax cable, and you may have to, depending on the size of the service area, have amplifiers, which are active devices. In this instance, because of the lost properties of fiber, we don't need the active devices in that distribution system. But to your point, from a map iconography standpoint, you could easily just change the letters in here, flip the triangle around, and you've got a node, amplifier, and distribution cable to get to your customers. So architecturally, it's not that dissimilar. Conceptually, it's just the components are different. Yep.
And I think that's one of the reasons that passive optical networks have been relatively well adopted, is because they look similar to kind of a lot of things that go on in a DOCSIS environment. And really, even over in the telco world, there's some analogs to this. It's not quite the same, but it's very common feeling. And when we get into building out PONs, your major components are right here on the screen. It's your OLT. This is an active piece of electronics that really starts the signal. It's the source of the PON network. Generally, it's going to be housed in a central office, data center, head end. point of presence. Today, these are going to be the GPON standard or XGS-PON. Those are your two dominantly deployed technologies today. Those are the flavors you can readily buy off the shelf. So your OLT, that generates that optical signal. We take a single strand of fiber optic cable, come out here to our magical splitter. This is a piece of passive gear that, again, does that port replication, if you will. These splitters, though, can be many different shapes and sizes. They can also be different split ratios. I come in with one fiber and then I leave with, it could be 1x2, 1x4. Eventually, though, we want to get it up to 1x32. That's kind of the standard that gets used in North America. But those split ratios can change even beyond that, and I got a slide that'll go through that. So a lot of variation here on what that actual product looks like, and then finally we have a single strand fiber optic cable going out to the home or the small business. That's going to terminate on an ONT, an optical network terminal. Another piece of terminology that you'll hear used out here is an ONU, optical network unit, and that's really, have I learned my PON lingo from the ITU? If you have, you call it an ONT. Or have I learned my PON lingo from the IEEE? If you're IEEE, you're going to call this an ONU. Common terms, or different terms, but the exact same piece of equipment. So don't let the T on the end of that throw you. It may be a U. But that terminates your signal. This is found on the customer prem, and it takes that fiber and typically drops off an Ethernet port. And today that can range anywhere from 1 to 2.5 to 10 gig Ethernet that we're going to hand off to the customer prem. There might be integrated voice ports on here, maybe a video port. ONTs, again, come in all shapes and sizes. So that's your basic PON construction. There's really 4 major components on the screen. Your OLT, optical line terminal, your splitter, your ONT or ONU, optical network terminal or optical network unit, and then we can't forget about single mode fiber. Single mode fiber is what makes all this happen. I've been in the business now since, God, I hate to think about this, 1999, and single mode fiber was one of the first things I learned about and the power of it when I got out of college and got into this industry. And without single mode, we would not be here having this conversation today. I don't know what we'd be doing. Hopefully I'd be, maybe on a beach somewhere having a drink, but somebody made single mode fiber and here we are talking about networks. So.
Well, that has really created a lot of opportunities if you think about it, pushing the nodes in the HFC plant farther and farther away, all of the technology that's gone into all the telecommunications infrastructure. It almost doesn't matter whether we're talking about wireline or wireless. Almost all of it travels through a piece of fiber somewhere.
Yep.
So if there is magic to be found, it's in that piece of glass.
Yep. There's so much power in the optical domain, and it's really, we're lucky because the optical pieces, the single mode fiber, the splitters, the passive components, they're the hardest part to install. That's where all the blood, sweat, and tears really goes in. But the stuff is so capable at the end of the day. This OLT, these ONTs, they can be swapped out and changed and improved upon as the technology gets with us. So that single mode fiber is such an enabler because there's such a high ceiling to the amount of bandwidth it can move. So to get back to the kind of active components, the OLTs, like I said, they can come in all sorts of different shapes and sizes. Adtran, we make these things. Here's kind of 4 of ours. And you can have everything from kind of a very dense fixed form factor like this box here. It's got 48 ports on it. This will house, 1,500 customers in 1.5 RUs, or excuse me, 2.5 RUs here. To some of our smaller footprints, this is a 2 RU box that will do just over 1,000 customers. And then you can do something that's completely ruggedized, ready to hang on a pole or strand mount. We've got 4 PON ports in here. That's going to give you 128 customers. So more dense things, all the way out to more rural. And really, the shape and size of your OLT is all going to be driven based on the environment that you're deploying it in. Am I in a dense, large head end where I've got thousands of customers that are feeding into there? Well, if you're in that environment, you're going to be looking at, this box here, a stack of them, or a chassis-based system like this that gets really dense, and you get over 5,000 customers on PON connections in this particular box. So the shape and size is really governed by where am I deploying, how many customers do I have to light up. If I'm in a rural area, I want to push out. Maybe I don't have a data center or a head-end location, but I have a lot of customers. I need to distribute my network. You can put these active components, like our sealed node, pretty much anywhere in the outdoor environment. And like I say, these get strand mounted often, but sometimes they're on, sitting in a ditch, the intersection of, Highway 2 and County Road 14 on a 4x4 post, and we got a hot spare in case someone slides into it with their Camaro because they're driving too fast on Friday night, God forbid. So all different shapes and sizes on the OLTs. On the ONT side of things, it's that same kind of variability, if you will. Kind of two of the core things, though, are we going to deploy our ONTs outdoor, meaning we're going to hang them on the side of the house? That form factor, surprisingly, has been very well standardized by the market based on this gray enclosure that you see here in this picture. This form factor for outdoor ONTs, especially this enclosure, is very much, whether we like it or not, a standard. The industry started buying this particular enclosure from Corning many years ago, and there are now millions of them hanging on the sides of houses. So manufacturers of ONTs like Adtran, if we're going to be outdoor, we want to be in this form factor that snaps right into that box. Because like I mentioned, with your fiber, with your splitter, that's a lot of set it and forget it stuff. We want to install it once. It's going to sit out in the network for 10 years. In the case of the fiber and the splitters, that can be 25, 30. This plastic box, you want that to sit there as long as you want to. That active technology inside it, you just want to be able to pop that out and swap that out. So if you're in the indoor on the side of the house, you're going to be looking at a form factor very similar to this. A lot of service providers, though, have moved indoor with this piece of with their ONT, mainly because an outdoor ONT can be 2.5, 3 times as much money, because all of these components are hardened, temperature hardened for heat and cool. This box has to be water resistant, and then you need to layer in additional lightning protection. That all drives up the cost of this active piece of electronics. If I can put the ONT in a house, it's temperature controlled. All of my lightning protection comes through the power panel on the home. It's all built in, so this is much more economical. But the big difference
Does this new tap satisfy the requirements for DOCSIS 4.0 deployment?
Yes, the upper frequency band of DOCSIS 4.0 goes to 1.8 gigahertz, but our tap has an upper frequency bandwidth of 2 gigahertz. This extra 200 megahertz of bandwidth ensures minimum roll-off in the upper frequency band. Also, the tap housing goes out to 3 gigahertz. This future-proofs your network when future technologies extends beyond the current 2 gigahertz we have here now. So you can simply upgrade with a simple faceplate swap. This is an extra insurance policy that the labor you use to upgrade your network now with a tap resplice will protect your investment for future technologies.
difference is anytime you got to physically go out there as a technician, if you got an indoor ONT that you need to troubleshoot, you have to make an appointment with that customer. They got to be there to let you in the house. That's why a lot of service providers, it's, ooh, this outdoor convenience. If I got to do troubleshooting on this ONT, the fiber coming into it, I don't need to make an appointment. So it's kind of two different camps there, but we see more and more service providers trending towards indoor. One of the other reasons is because they're trying to do more inside the home. Deployed, managed Wi-Fi service, video services. You guys are going to be very familiar with that. So the ethos is, well, I'm in the home already. I'm going to save a couple $100 per ONT and just schedule that appointment and kind of perfect our scheduling skills. So indoor and outdoor, those are two very big distinctions. But you've got port variability, how many Ethernet ports are on these things, how many voice ports are on them, do they have video ports on them, and then we build more bespoke ONTs for different applications like a small business. This particular ONT has 2 gigabit ports on it, 8 POTS lines, because businesses, we need 1 or 2 data uplinks, but we need multiple phone lines. So 8 POTS ports in this ONT, God forbid the customer is still ordering this, we can deliver 4 T1s on these ONTs. So a lot of variability has gone into this ONT space.
I think we may need to define POTS lines, Greg, for some of those that may not heard that. That would be plain old telephone service.
Yep.
The common acronym for just traditional telephone lines. Yeah,
absolutely. Thank you for that. And FXS port, that's another one you'll see on the cut sheets, but those are the voice ports. This is where you would hook up an analog phone set. And small businesses, they still need lots of phone lines. So you definitely, when you're getting into small business applications, data is very much important, but those phone lines are still in demand in the small businesses. And then other things you'll see is different packaging. For an MDU, you'll have different enclosures where you can house multiple ONTs in a very small space because you're trying to wire up an apartment building and you've got multiple customers that you're going to anchor back in a small wiring closet. The building owner calls it a wiring closet, but we all know it's the janitor's mop closet, right? That's the kind of things you run into. So you have to have the appropriate accessories to get these ONTs deployed out there.
So I think it's important to talk about, as we think about PONs, the passive is the first word in PON. And that's very important from an operating expense perspective and a reliability perspective in the outside plant, because it doesn't require any kind of voltage from the commercial electrical grid or a power supply or battery, the battery bank, to manage the distribution piece between the OLT and the ONT. However, those two components that we just talked about are both active components, which do require power to run. Now, in the ONT perspective, that's offloaded to the customer at the premise, and it's not a ton of power to power an ONT. But in the external application, that's one of the considerations, right? In addition to, you mentioned the environmentals, the water resistance, the temperature hardened, but you also have to route power from somewhere in the customer premise out to the ONT, because it is an active device. So while the distribution portion of the system is passive, no optical transport network, whether it's HFC or a traditional FTTX system, does require some active device somewhere to transmit and receive the optical signals.
Yep, so that's another reason that service providers have moved indoor, because there's more readily available 120 volt power points, right? Or wall sockets. Outdoor, that's a bit of a beast of a problem, especially if when you're approaching it the first time. There's a lot of different ways to kind of solve that issue. Some of them, ironically, involve putting a UPS indoor. So that first appointment, you still got that scheduling to do. but you'll put a UPS unit on the inside of the home, put that on the home's power, and then drive it's actually a 7-conductor telemetry cable through the wall into the outdoor ONT. So that's one, yeah. There's a lot to think about when you're talking about powering these ONTs at a home. Typically, the most surefire thing, and it really depends on region and climate. It always surprises me the number of service providers that put ONTs in garages and just make that their standard. But they're all located in the Southeast and in Southern California. And the reason for that is, I think, twofold. They don't all say this one. To treat their technicians better, they can get them in the customer's garage and get them out of the sun. But really to keep the sun off these devices. Heat is as bad or much worse in most cases than cold temperatures on these ONTs. Heat-related failures are more significant. So a lot of service providers will take an outdoor ONT and put it in the garage, and then the powering problem gets a little bit simplified. Other solutions, if they are sticking towards the traditional utility entrance that's right next to the power co-op's meter, there are actually power rings that you can source that your technician will actually pull the top of the meter off, pop the ring on there, and then the meter goes back on the ring. And then you have a power lead right off the main meter that's at the home that you can wire into your outdoor ONT. So a lot of different solutions out there for powering outdoor ONTs. And then, to kind of bring up the voice ports, the POTS ports again, if you choose to do voice service, your ONT, you may or may not need a way to provide battery backup for these. Depending on your relationship with your local controlling entity, the government, whether it's a county or city government, they may or may not require you to provide battery backup for these. By and large, you have to make available a solution that the customer can buy from you to do battery backup of voice ports for 911 service. But there's still a lot of places in the country where it's the service provider's responsibility to put this on a minimum of a 4-hour UPS. So whether it's indoor or outdoor, if it's got a voice port on it, that's something you might run into. I'm installing as many UPSs as I am ONTs because we're still dropping voice service off. So a lot of different little wrinkles there.
Yeah, a lot to think about with ONTs and what's going on at the customer premise, whether it's a residential installation or a business or an MDU installation.
Yep, absolutely.
Okay, what's next?
So just to kind of, we talked a lot about the active pieces, OLTs, ONTs, and really talked up the splitter. It's that magical piece that gets us all those extra ports. So I better show you what these things look like. Again, just like the ONTs and the OLTs, there's all sorts of different permutations of these. It really comes down to cost, craft friendliness, and what your company's kind of approach is to mass deployment of fibers. Right here, this is a pre-connectorized splitter. That's 32 ends. And then this would, this magic black box here, that's the splitter itself. That's going to be put in a rack mountable holders of some point, typically done in a rack. And then you route these 32 cables over to their final destination on some sort of panel. One of these leads will be that lead that comes in, and then the other 32 will go out to the customers. And then again, same concept, just different form factors. Here's a very basic 19-inch 1RU panel. You can see we've got the incoming fiber feed here, and then that is divided out amongst these 32 connectors. This is where we'd patch in our drops out to our customer. These cassettes up here, again, just a modular way of doing this. So all sorts of different form factors for the splitters. These are by and large going to be in a central office or a cabinet. But as we'll see in a couple of slides, you can distribute these things too. So splitters, not only do they vary in size and form factor, you buy them in a set split ratio. So the 1/32 split ratio, that's one fiber coming in, 32 fibers going out. That's pretty typical in North America. But like I mentioned, you can go up and down. We have some customers, some service providers, they'll actually go down to a 1/16 split. So they'll be doing one fiber in, 16 out. They'll hang 16 customers off here. And they'll use that to control congestion on a GPON port. So the GPON standard gives us a total of 2.5 gigs of data to share. We're going to hook up 32 homes. If they start gobbling up all of that 2.5 gigs, we can actually split then that port and change the split ratio from 32 to 16, and then they'll have twice as much bandwidth because we have half as many customers there to work with. So this is kind of atypical, but it is a way to deal with congestion on a GPON port and get more life out of a port that's been installed, as opposed to just saying, oh, I've used all my bandwidth, I have to buy a new OLT from somebody. This is another way to just kind of provide a path forward if you're getting congestion on a shared port. The other things is these will go up in ratio as well to 1/64 and 1/128. So one fiber in, 64 out, and 1/128, one in, 128 out. 1/64, relatively rare to see that deployed in North America. Where you will see this is in MDU builds or very dense urban environments where a service provider is, these are very small homes. People don't spend a lot of time there. I don't typically see a lot of usage. They will aggregate them into a 1/64 splitter that not only saves a little bit of cost on the splitter, but then I've got twice as many subscribers going into that single port. And then finally, there's 1/128, exceedingly rare in North America, but very much common in international markets. China uses a lot of 1/128, Pakistan, India, high density, high population areas, and a lot of emerging markets. Because in those emerging markets, they're going to be thinking, okay, my average user, not home all that much. The internet isn't the central focus of their life like it seems to be for so many of us here in North America. I don't know if that's a good or bad thing, but they'll be buying less bandwidth. So on a 1/128 way split in an emerging market, you might be doing 20 meg services max. Where in North America on a 1/32 or a 1/16, you're going to be selling symmetrical gig services. So this is one area where you can kind of leverage the outside plant, make a few subtle changes, and that is something that's going to ripple all the way back to, your marketing department and the packages that you're selling. So interesting approaches that can be used here. But typically North America, 1/32.
Now, when we talk about split ratios, there's more to consider than just, the available bandwidth to that subset of subscribers. We actually just wrapped up a series on passive devices on the HFC side of the plant, where, passive devices are really power dividers. So there's, in optical terms, we talk more about ratios than we do with losses, but there is a relationship between the split ratio and the total optical power loss through that device. And that has some design considerations too, right? In our link loss budget. I think we're going to talk about that later, but it's one of the things when we talk about splitter size and the choice of splitters is actually that power divider loss. So here it is.
Yeah. as you go up in splits, you are going to lose, it's going to attenuate more of that light coming down the fiber. So that's another thing to think about when you are considering, hey, we're going to go build PON in a new area. This is going to impact how far you can go. That's one of the reasons 1x32 is more dominant in North America. Yeah, we're selling more bandwidth here, typically charging a little bit more revenue, but also this is a big country. I had a friend from Poland come here and visit us in Minnesota, and she was just, I can't believe it takes 8 hours to get to Chicago from Minneapolis. Like, yeah, go west and try to get someplace important. It's going to take you 14 hours. So, whether you're in a city like Chicago or you're in a rural area like Minnesota or Montana, we have a lot of space, a lot of distance to cover. We are not that dense by comparison. So we need to reduce our light budget in a lot of cases to meet our distance needs. That's where, when you get up to the 1x64s, 1x128, you lose a significant amount of additional light at 21 and 25 dBs. And we got a little worksheet we're going to share with you, and you'll see kind of how that peels out really quickly.
So the good news is the fiber cable itself has relatively low attenuation loss when compared to like an HFC or coaxial fiber. There's actually a lot more attenuation, per kilometer or 100 feet or whatever as opposed to fiber. So one of the primary considerations in calculating your link loss budget is the size of your splitter. Because the fiber attenuation of the sheath footage in the network is actually much less impactful in that design discussion.
So yeah, in that design discussion, you've got a few tools built into the PON standards themselves, all the APON, BPON, GPON stuff we talked about. As those standards are described, they are targeting a 20-kilometer PON length, and that is the maximum length between your OLT port and your furthest ONT, 20 kilometers. So the standards have that sort of a light budget built up for you, but as you look at different optics and OLTs, different optics and ONTs and ONUs, manufacturers like Adtran have figured out ways to extend these things. So the PON standard says 20 kilometers, that's all we care about, that's all we're going to standardize. Manufacturers, we've all come up with ways to go a little bit further. So 30 kilometers, 37 kilometers, we call those extended reach modes. They're pretty typical. And then you can get into some very extreme corner cases where you can actually, if you back off your splitter, you can repurpose some of that light budget into strand distance and get all the way out to 62.5 kilometers. That's our extreme distance use case. And this is very important. A lot of areas get built out, and then there's, especially in rural America, there's that one farm that's just way off the beaten path, but we need to get service to them. They're 30 kilometers past my last 20-kilometer PON. So that's when I start to say, hey, I'm going to do a 1x4 or 1x2 splitter and get into these longer use cases. It's very much an extreme example in a corner case, but time and time again, you run into those in exchanges, and being able to kind of make that exception, if you will, allows PON to be adapted to a lot of different installation needs, if you will, deployment needs, I should say.
Don't forget that fiber to the farm. It's very important to our agricultural community. Speaking as a farmer. Fiber optics, as I mentioned, like you may be 0.25 dB per kilometer of loss in the 1550 nanometer range. So most of that loss is splitter loss. So the difference between a 20 kilometer and 50 kilometer is not excessive from a fiber path attenuation perspective. So the majority of that loss is in the splitter itself.
Yep. And like I say, when you go for these longer use cases, and really 30 kilometers is pretty much a standard for all the OLT, ONT vendors out there. Everyone's really building to that from, as an OEM kind of vendor. Us in this situation, like Adtran, if we don't build a product that goes 30 kilometers, we're kind of going to be sunk. 20 kilometers is the standard, but you start playing with these ratios and you can move that light budget around and convert splitter ratio into fiber kilometers to get those longer distances. So other things that get considered as you're building out these systems is how are we going to house or architect our actual splitters? There's a couple of different schools of thought on that. One is a centralized split. This is where I bring all of my splitters back to one location. That's relatively close to my OLTs, my active components. And then I essentially run a home run fiber out to each home. This is kind of by today's standards, this is kind of a Cadillac. The nice thing about it is you have all of your splitters in one location, but your fiber reach here, these are going to be 20-30 kilometer runs out to each house. So you're not being very efficient with your fiber.
Right.
You get some great craft friendliness. All the technicians are going to be in the central office. If they need to work on splitters, to clean a port, to move a customer from one to the other, to replace a splitter. That's one reason service providers choose this. The other advantage you get here is if you have a customer that converts from, okay, I was a residence, but now I've built a pole shed and I've started a business of whatever sort, or I've gone from being a hobby farmer to a very intensive boutique farmer of some sort that has actual business at their location. You want more bandwidth, we can actually take that home run fiber, pull it off the splitter, and then maybe back here somewhere we have a point-to-point connection that you could dedicate a gig or 10 gig to that customer. So that was really in the early days of PON what drove service providers to centralized splits was, well, we're doing BPON. That's 650, is it 655? I'm going to reserve the right to be wrong. It's either 655 or 622. I can't remember right now. But that wasn't a whole lot of bandwidth to share by 32 accounts. So service providers are like, yeah, that's not a lot of bandwidth. If this PON thing doesn't take off, I want to be able to grab that fiber and just plug it into an Ethernet port. So yeah, they were kind of hedging their bets. Today, they do it in terms of it's really convenience, craft friendliness, having everything centralized in one location. And the housings for the splitters really start to change. When you're doing that centralized split, that's where these cassettes kind of start coming in, and then you have these very advanced panels that get rack mounted. And actually, these examples are rudimentary, but if you see this deployed, if you're in an urban area, you're going to run into this. Just because they're aggregating so many fibers. It's just racks and racks and racks of managed fiber. And companies like Corning, CommScope have really, put pen to paper and done a lot of thinking about how to do this optimally. So these are all different examples of very dense centralized split systems. This frame down here, there's probably 20,000 customers on this frame. So it's a huge deployment, but crammed into a lot of indoor space and centralized. What a lot of systems, though, end up being is what we call a cascade or distributed, where we're taking our splitters. We might have a 1x2 split in the central office next to an OLT. Maybe we don't have any. But then we're going to cascade out splitters along our fiber route and build into having a target split ratio. So again, 1/32 would be your ultimate split ratio. You'd end up with 32 ports. These splitters are on 3rd Street, and then we go another block up to 4th Street, and we've got 2 more splitters. and we're covering 32 homes. But we've cascaded these out. Sometimes a service provider they don't have enough room. Their point of presence, their head end is very small. They can house their OLTs and a few others. There's just not room for splitters, so they'll push that into the outside plant. When you do that, your form factors start to change radically, but they go in a lot of the common telecom tooling that pedestals, outdoor housings, they're in ruggedized splice enclosures. Other things that can happen is that these will be pre-connectorized. So you splice this up once, and then these ports are modular. You don't need to splice in. You can just snap your next fiber drop into this sort of fiber splitter here. So these are highly engineered, pre-built, but we've got other use cases where we're going to build everything in splice cases. We can buy very raw components. This is a 1x32 splitter that's got 32 bare ends. We would need to have a very efficient technician that's great with the fiber splicing, and they can build that into this splice case. So different service providers take different approaches depending on really the technicians that they have, and to get a skilled fiber splicer, that's not cheap. So if they have those folks on staff, they're going to want them doing this. We've got a couple of top fiber splicers in the field. We're going to leverage them. They're going to be, putting fiber together all day, every day to earn their paycheck.
Now, go back to that distributed fiber kind of design drawing, because that starts to then look like the more traditional HFC network. And from an outside plant perspective, this allows the operators to leverage their fiber assets without having to build the dedicated home run drops from the aggregated splitter location. You can take your single strand of fiber that's leaving the head end and going out to a neighborhood, and then add your splitters out in distributed points in the architecture. And it really, again, if you were to flip the splitters around and point the triangles the other way, it looks a lot like a traditional HFC network. With you could call that first leg of the splitter or fiber out of the head end that trunk of fiber to your first splitter location, and at that point those other fibers off the splitter become distribution splitters to a fiber tap, and then it's just connecting to the fiber drop system. So there's a lot of similarities, but the way you interact with it, or the need to interact with it, quite frankly, is very different. One of the primary benefits that we haven't actually talked about with passive optical networks over HFC networks is, one, the lack of the necessity of outside plant powering, right? Because it is all passive. But two, the susceptibility to electromagnetic interference, over-the-air energy, those other kind of things, because it's all light. It's not as susceptible to interference from other energy sources that exist over the air. So that's one of the really cool benefits of PON over HFC. But architecturally, if you think about this distributed splitter kind of network, it's really not that much different.
Yep. Yeah, there's some real strong analogs, and again, I think that's one of the reasons that PON has been successful. These splitters are so adaptable. They build them in a million different shapes and sizes so they can go anywhere. And odds are that the vendor that's doing your HFC system, they've thought about that. It's like, my business is going to shift to fiber too. How am I going to participate? So they'll have snap-in splitters to some of their existing gear.
And when you look at that pedestal scenario that you had, I think on the next slide, we see pedestals like that with coax coming out of the ground and an 8-port RF tap. Mm-hmm. This is really an optical distribution cable going into an 8-way splitter, but it's effectively an 8-port optical tap.
Yep.
And so your drops would just, transition from, Series 6 coaxial cable to a single mode, optical fiber cable that you could attach right up to that tap.
Yep.
So a lot of analogs to the HFC world.
Yep. That's what a lot of folks appreciate about the pre-connectorized is, it's not an F connector, but it's this, we just pop it in there, and these are half twist, twist lock mechanism. You just pop it in there, and then you're focusing on the big job. The big job is burying, 100 feet, 200 feet of cable, right?
Yeah.
And anyone can just come and plug this in. I don't need to have my fiber trailer out there or my handheld fiber splicer. These are really a huge time saver. But like I say, we've got a lot of service providers that have very skilled technicians, and they'll put them to work building these too. Another reason that you might choose more of a raw or bare type of componentry on your splitter size is you've just got a razor thin budget to get an area built out, and it might not make the best long-term sense, but we're going to look and find the least the least expensive components that we can, knowing that we've got people on staff that are I'm going to pay them X number of dollars, whether they're doing fiber splicing or, tuning up the work truck. So a lot of your independent operators tend to get into that situation where they I'm going to keep my OpEx or my CapEx as low as possible to deploy this new area, just because I have to, because that's what the bank is looking for. There's oftentimes really weird financial reasons that you'll get into that. But pre-connectorized, that's, if the budget supports it, that's really the way to go, because your operating cost over time really gets reduced. Making moves, adds, and changes here, especially if you're not connectorizing these, you're just fusion splicing, locking everything in, then it gets really expensive to go back and make a change. So we talked a little bit about that optical link budget, and here's some numbers, and these are our theoretical max distance worksheets that we use at Adtran when we work with customers. And you absolutely have a defined optical budget in those GPON, XGS-PON standards, and they kind of were set in the APON, BPON, GPON days, and they'll just move forward with us. Optical budgets, you've got two wavelengths, 1490 and 1310. We're thinking about GPON here. 30 dB on 1310, 28 on 1490. But this varies. So the standard says one thing. So that's what a manufacturer like Adtran, we need to adhere to that standard. So when we hand you optical equipment, it's going to cover your 20 kilometers that you built. We're two different entities. Adtran, we don't do, and really the majority of my peers, we don't do the passive components. You're kind of good at the active stuff, or you're good at the passive stuff. There's not a whole lot of crossover. Which has always surprised me. But if we're two different ships traveling down the same river, we want to kind of get together and get to our destination in sync, so we adhere to those standards on the active side, and the passive component makers adhere on the passive side. I'm creating light with my active equipment, and the passive components are attenuating it. That's the way it works. So we've got an optical budget, but the thing you need to remember as you get into this, you do need to look at your specific OLT port that's injecting the light, and then your ONT port that's going to be receiving that light on the far end. They're going to have different specs. Now, your manufacturer should have done the right job and stayed inside the standardized optical budget, but it can vary from manufacturer to manufacturer, or really from OLT part number and ONT part number. At Adtran, all of our GPON ONTs have the exact same optical specs, but when you get to XGS-PON, the numbers are a little bit different. So you build out that optical budget based on the equipment that you're deploying, the active equipment, and then in this kind of back of the napkin type of calculation, we put in just loss assumptions for the specific. In this case, we've got a range of splitters, and then we are doing attenuation values at the different wavelengths for the fiber itself. So we've got a 0.18 per kilometer dB loss at 1490, and then we've got a 0.33 loss at 1310. Now, again, these are assumptions that we make as we're doing this particular design, but you can go to your manufacturer and they will give you their expected performance numbers. I know when I used to sell a lot of single mode fiber, everything that we built was either based on a 0.25 or a 0.35 loss level, and we would talk with the customers. Okay, what standard do you want me to use? 0.25, 0.35. If we're feeling a little brave, we'd do 0.25. If we wanted to be more conservative, we'd run our light numbers at 0.35. So you can do the same thing for PONs. Your fiber manufacturer can tell you what these values can be. These are just kind of loosely accepted values when you're doing these kind of calculations. So we've got this in a spreadsheet, works all the math out for us, and our 1490 value on a 1x4, it's 117 kilometers. That's really far. But it's only 70 kilometers at 1310. And I need to transmit and receive at both, so my smallest value is what I have to take as my max distance. So 70 kilometers, that's really in there with that 62.5. The math works out that way. As we spec out our equipment, we kind of back that down a little bit. That's why it's always fun to work with customers and kind of review what they've been able to pull off. Oh yeah, you say 62 kilometers, but I'm actually doing this. Yeah. One thing to note about the PON OLTs and ONTs, especially at these longer distances, again, these are kind of those rare cases. But once you get beyond 30 kilometers, then your OLT actually needs to go into an extended reach mode. And it's not adjusting the optical end of it, it's adjusting the timing of the link. Because you've got that extra distance, it's going to take that little extra fraction of time, and your equipment needs to be told, hey, you need to compensate for that. So the OLTs and the ONTs absolutely need to support it. Today it's kind of table stakes. Back in the earlier days, though, that was something that was kind of novel.
At the end of the day, though, our theoretical maximum distance is largely governed by the size of the splitter. And the size of the splitter is largely governed by what population of people you're trying to serve, as well as how far they are away from, your OLT or your core. So a lot of things to think about, but really, fiber is very predictable when it's operating in an unimpaired state. I think the quality of the optics, as well as the optical components like the splitters, and even the splicers, have gotten so much easier, faster, better, lighter. I remember when I started back in 1990 something, to buy a Fusion splicer cost as much as my house.
Yep.
That's a true statement. There were, I remember Fusion splicers back in the 90s costing $50,000, $60,000, $70,000.
Yep.
I paid less than that for my first house. And today they're, a couple $1,000s. They're battery operated. You can almost stick them in your pocket.
Yep.
But the quality is amazing. So, when we're thinking about troubleshooting, if I have a low light scenario at an ONT at a customer premise, these are some of the things that I need to think about, right? What is my total fiber distance, and what size splitter or combination of splitters in that distributed splitter model, and those go into your total link loss budget. And then all else being equal, if my transmitter is putting out the right optical power, there's a reason why I'm not seeing my minimum light level at the receive device. So all important things. So thanks for throwing this link budget in the description or the discussion here, because as a technician, this is super important.
Yep. And one, I know light levels on PON, very important. Keeping track of them is very important. Our NMS for our equipment actually keeps track of and will put light levels in front of, the newest customer service agent and color code them red, yellow, and green. Light levels are key. There's another spec out there that's called a BIP error, byte interleave parity error. And this is something that's been with us in the optical space since the Sonnet days, which is, you're getting back to the 80s at that point. But that is also one of the, you can see transmit and receive BIP errors in these systems. And you can, if they're rapidly incrementing, whether you're on the transmit or the receive side, your customer and your ONT might think it's not getting enough light, but if you're rapidly creating BIP errors, that number in and of itself can tell you, hey, you've got a dirty connector on the OLT side or the ONT side, depending on if you're seeing transmit and receive BIP errors out of the OLT or the ONT. So that's one area for troubleshooting that we put right front and center in our NMS, alongside the light levels that these optics are reporting. We have those BIP errors in there on a counter, so you can see that as it's happening. And if my light levels are bad, but my BIP errors are going crazy, if I am on the receive side of an ONT, I'm going to dispatch a tech with a cleaner, because some dirt or gunk most likely got on that connector. That's what, 9 times out of 10, that's what generates those BIP errors. So that's kind of a little inside baseball piece there.
2 things for those who may not know what NMS stands for. Why don't you define that for us?
Network management system. That's the piece of software that we install, or our partners install, our customers install, to look at all the statistics that the equipment is delivering and do the provisioning of it.
Okay. Secondly, what's interesting to me about PON is, for somebody that grew up in the HFC world and our earliest nodes were analog, like if we saw light levels below like -3 dBm, we started to get nervous, right? Because you're drifting into failure territory. It wasn't entirely uncommon to see like return receivers in the head end operating about -9, but that still made you anxious. Today we're seeing at some of these ONTs and these optical systems, light levels in the -20 range that are perfectly fine.
Yes.
And that has a lot to do with the data transport methodology is just very different than like traditional analog intensity optical modulation, right?
Yeah, you're delivering kind of a different package going from analog to digital, and the amount of error correction that you can do plays into that. So the transceiver, the actual optic that's in these, I don't want to call them low performance, but they're more efficient than they were back in the day.
Yeah, for sure.
It's kind of like a kick-ass V8 versus one of the electric motors in a Tesla.
So just a couple of things for technicians to think about as you're migrating into PON, maybe for the first time. The range of acceptable optical levels based on your link budget is just very different than, say, even something like an RFOG system, right?
Yeah.
They're just very different technologies and different considerations and troubleshooting. So awesome. Thank you for that optical link budget example, Greg. What do we have next?
So other things to explore. One thing that I kind of touched on that I want to get into really quick is some of the economic pieces. This is a big thing that has driven PON for us and gotten a lot of service providers to adopt it. We talked about the splitter does a lot of, magical port replication on the fiber side. So our point-to-point deployment, it starts to look like this. the fibers are 1-to-1 between your switching and your client device, between your OLT and your ONT in a traditional point-to-point system. You got 32 strands to do 32 connections, and if these are each a mile apiece, you've got 32 miles of fiber. But really, when it's not that raw fiber that adds up. The splicing cost definitely starts to add up. But if you're doing a net new install, the cost between 32 strand or 48 strand is really not huge. If you're an existing installation though, and we talked a little bit about this earlier, if you've got, maybe you're fiber limited, this isn't even possible. Where with PON, you can leverage one strand, put that splitter out, and then have a base of operations for, 32 ports. Point to point, where you really spend a lot of money is those optics itself. This is, every home has its own set of optics. And if I'm doing point to point, I need a mirror to that in the head end. So this is where you get a big cost savings, is that you can eliminate 31 of these optics. You're still going to have 32 out at the home, but you're just going to have one here at your head end. So it really comes together optically in a much more efficient manner. And that's one area too that customers are like, well, we still have to pay for the splitter. Yes, you have to pay for the splitter, but really 2-3 optics back here on your OLT side cover the cost of that splitter. So this becomes a major cost advantage, and it's not really the amount of fiber that you're saving. The splitter doesn't upend the economic apple cart, but where you save is these receivers on the OLT side. In that central office in your head end, you just have one compared to 32 out in the field. So you can really cut that out, really cut that cost in half. And this is where the cost savings of PON really comes in. That's why that centralized split we talked about, it's like, oh, that's not the most efficient use of our fiber. We could cascade things, save some fiber miles. Really, at the end of the day, there's not a whole lot to be saved in that raw fiber. But with PON, what you're saving are these optics. That's thousands of dollars on a build. If you were to compare PON to active Ethernet. Another area where where cost kind of escalates and shows a big difference is your number of splice points. When you're splicing together a point-to-point system, if everyone's got their own fiber, to do 32 homes, you're looking at 128 total splices. We're eliminating optics from the PON OLT side, so that's going to eliminate splices. So I can drive out, I can drive down to 66 total splices. I lose 32 splices on my head end. I lose 31. I lose another if I have an intermediate point. So I can drive a lot of those splices out. And if you have splicers on staff, maybe that doesn't matter to you. But if you're hiring a contractor to do your splicing, or, splicing can be expensive. It can be $100, $200 per burn. And then considering the time and effort that it takes, being able to reduce that job, that can help save you some of that upfront CapEx costs when you're building these networks. So
yeah, you mentioned that
economic factors in there, absolutely.
You mentioned that earlier, where all of the blood, sweat, and tears and largely the expense comes in at the construction point of building this network. Because once it's all up and running, there's really not a lot left to do, except for potentially troubleshoot if something happens, because that's one of the beauties of PON is that the operational expense of managing it once it's deployed is negligible compared to the OpEx of an HFC plant. but compared to the capital expense of building it, obviously that's where the vast majority of the expense comes in, whether it's materials or labor. So a lot of things for companies to think about when they're designing and deploying these networks to get them operational, and then sit back and relax and enjoy the benefits of having it once it's running.
Yeah. Yep. Well, and you don't sit back and relax, right? You go and you build another one.
Well, that's fair. It's never ending, and especially now, there's been a lot made over the last few years of building out the infrastructure of America with something that is really defined as broadband, but that definition continues to expand.
Yeah.
As the consumption needs of the country increase. So you're right. We're never going to stop building. The question is, what do you build? And how do you build it? Whether we've seen even on the HFC side of the plant, leveraging DOCSIS 4 to add capacity and bandwidth to the currently existing HFC architecture, or we talked earlier about the migration of different versions of PON based on the ITU or IEEE standards to try and leverage the existing fiber assets to get more capacity. So let's talk about that. The differences in the PON prefixes. You did touch on, APON, BPON, but the great thing about our industry, I think, whether it's on the coaxial side, the copper side, or the optical side, is standardization, whether it's ANSI, ITU, SCTE, IEEE.
Yep.
There's been a lot of really good work going into standardizing these technologies. From an educational standpoint too, you and I were talking earlier about how different the network is today than it was when we started. Both of us starting in the 90s. Today's technicians could see, on the traditional HFC side of the house, sub-split, mid-split, high-split, extended spectrum, DOCSIS 4, full duplex. On the optical side, they could see RFOG or different versions of PON, EPON, GPON, XGS-PON. The diversity of architecture is a benefit to the customer base in America, because there's so many different technologies that ultimately, whether they be wireline or wireless, to connect America to what's important to them.
Yep.
But as a technician, it just means we have to understand more acronyms, terms, technologies to be able to troubleshoot them, to interact with them, to install them, to service them. Yep. Because there are some slight differences. So let's talk about that.
Yeah, that base understanding that you need to have today versus the early 2000s, it's a whole different ballgame. And like I come from kind of a telco background, and when I first got into the business, there was a ton of copper, ton of TDM, lots of T1s, and ISDN, dial-up was a thing, all that stuff. And today, I hate to say it, but a lot of that stuff still exists, still gets troubleshot, still generates trouble calls because customers don't just give those things up. Yeah. So as a technician, your challenge is, especially if you've been in a network that's got some history, and there's a lot of them out there that have been slinging service for a number of years. You're gonna, you have a lot of different core competencies that you need to have, because as that network evolves, it'd be great if we could just overbuild ourselves, every time we thought we needed to. But the fact of the matter is, we evolve into these things. We can only do so much at one time. So we need to leverage what we've built in the past as long as possible. And that means, sometimes we got to saddle up and ride a copper solution a little when the rest of the industry is saying, oh, you should all be fiber. Well, I'm sorry, but for a lot of customers, it's still an upgrade when we can go from DOCSIS 3 to DOCSIS 3.1. You know,
Yeah.
there's benefits to be had there.
Well, and as
you
an
gotta
operator,
Yep.
you got to leverage the assets that you have deployed
Yes.
As long as you possibly can to, return the value on that initial investment.
Yep.
So,
And build cost, it's not getting any lower. So there's a lot of standards that have been built up around PON. I showed you some of them. The IEE, sorry, that's a typo. IEEE. Your standards bodies are the ITU, International Telecom Union, and IEEE for the dominant standards in the PON area. And really the biggest variation around all of these standards are the number of megabits or gigabits that the technology that the standard can deliver and the wavelength that it runs on. Understanding the wavelength across different generations of PON can be very valuable because it helps you understand how these things can be layered together and how they, today we are truly layering them together on the same PON. So GPON, the most widely deployed of the PON technologies, 1310, 1490. Two big chunks of frequency. As we evolved from 2.5 gig to 10 gig into XGS-PON, different frequencies, 1577 and 1270, much narrower. I'll also have you know that there's another little standard out there. GPON, XGS-PON are governed, standardized by the ITU. EPON, or Ethernet Passive Optical Networking, this is the IEEE standard. And there's EPON and then 10 gig EPON. These have been around for a while, have been running at the same wavelengths as ITU XGS-PON. So there is a conflict there. But the ITU is very thankful for EPON, and it's running in 1270, 1577. Because as we migrated away from GPON, XGS was not the first place we tried to go. The first place the ITU tried to go. We had a standard called NG-PON2 that ran at multiple wavelengths in the 1500 nanometer space, between 1524 and you can see 1602 here. This standard largely failed. So this was a 10 gig standard. We're going to go from the 2.5 gig of GPON to the 10 gig of NG-PON2, but we're going to be really brilliant with this. We're going to start to inject WDM channels, so I can run up to 4 or 8 instances of these PONs on different wavelengths. That's why I have the range here, simultaneously. So the end game here was you could potentially get 172 gigs of bandwidth with this NG-PON2 idea if you were able to fully build out the DWDM characteristics and channelize this chunk of spectrum.
help me out with the
Yep.
TWDM. I've heard CWDM and DWDM, coarse wave division multiplexing, and dense wave division multiplexing. What's the T stand for?
So when you talk TWDM, that's just talking about I've got a TDM technology running in a wave on a wavelength. So at its core, GPON, XGS-PON, EPON, these are TDM technologies. They are perfectly timed out when it comes to actually transporting the packets. and when the ONT and the OLT, when they'll kick on their transmit and receive lasers. That's all timed out. That's the time division multiplexing of it. When you apply that to a wavelength, that's when we as an industry start saying TWDM. So it's a combination of TDM, time division multiplexing, and wave division multiplexing, all packed into one nice little telecom acronym.
Now, what's also interesting about this is since they all use different wavelengths, well, with the exception of XGS or EPON, they don't conflict. So you could potentially leverage a single fiber to transport either GPON and XGS-PON, or GPON and EPON over the same fiber.
Yep. And today we're delivering GPON and XGS-PON out of the same port, off the same optic, on the same fiber. That's very common today. Now, you do have a conflict between EPON and XGS-PON. So like I said, ITU very thankful for these wavelengths of EPON. EPON's been running in this wave space for a long time. ITU didn't really want to encroach on it. But when NG-PON2, this is a lot of fancy technology being packed into a $100 ONT that's going to go on the side of a house. That optic, if we're going to be able to choose from 4 or 8 different wavelengths, that needed to be really efficient. But the technology never really evolved to a point where it got... it was always cost prohibitive to deploy this, because these optics, having this variety of optics running in these channels, was very expensive. So what the ITU said was, well, we're going to take all the coding, all the data bits of the NG-PON2 standard, but then we're going to borrow the optics from EPON, because in Asia there's a boatload of EPON and these optics are very economical. So that's where we're going to run XGS-PON. So the coding, the bandwidth delivery, exact same between NG-PON2 and GPON, but we're running it at different wavelengths and we're only doing one fixed instance of it. And we borrowed, they're the exact same optics between EPON systems and what became XGS-PON systems. So one thing that did survive out of the NG-PON2 standards is there's a chunk of wavelength up here in 1620 nanometers that does point-to-point channels over PON. We're really inside baseball at this point, but this is a cool application where you can run 4 transmit and receives in a point-to-point fashion over a splittered network, and that kind of gets you a virtual point-to-point cable that you can install over a PON network. That was built out in the NG-PON2 standard and being deployed and used today. It's a niche application, but it is something cool.
That is cool.
Yep. All of these wave spaces are interoperable. The next big thing in PON is 50 gig PON, and that is really starting to evolve, and we're getting into trials as we speak. XGS-PON really overtook GPON in kind of pure port sales back in 2022. So you're kind of like, wow, XGS-PON feels really new. Well, we've been doing XGS-PON trials since 2016, so there's a run-up to it. We're starting that 50 gig PON run-up right now. There's some existing trials. We'll be doing some ourselves this year. But really, in 2025, and then by the time we get to 2030, that's when we expect 50 gig PON to overtake XGS-PON. So in this diagram, it's kind of written out roughly. 50 gig PON is going to run in a space that's occupied by GPON, but the standards really flesh this out nicely for us and give us some options for 50 gig PON where we can run it in different wave spaces and avoid GPON or XGS-PON if we need to. So upstreams and downstreams are here, and then you have the upstream and downstream for GPON and XGS kind of over here on the right of the spectrum. Our upstreams are here in the left, and then you have 3 different options for 50 gig PON. 1620 to 1280, that's kind of standard operation if you don't have XGS-PON to worry about. If you have XGS, you could shift to the 13 to 1310 space, but that's going to conflict with GPON. So if you have both, they have a notched out option for us that runs between 1280 and 1290. These optics here will be a little bit more expensive because that is a very narrow chunk of wavelength, but this is a way to get all 3 technologies on a network at the same time. So simultaneous, we call that coexistence when we're running these different generations at the same time. And that's definitely definitely a feature set of the 50 gig PON standard. And like I say, we're doing that with the XGS and GPON today. So
well, that's the benefit of standardization, right? With governing bodies like IEEE or ITU, is the ability to develop standards that allow for that coexistence. From an operator space, that's hugely important to continue to leverage the fiber assets that you have deployed, but to migrate technologies without having to do an overbuild and incur that capital expense of construction again.
Yeah. Yep. And when we first started transitioning from copper to GPON, or coax to EPON, whatever it might have been, from copper to fiber, you had 2 parallel networks. You had to build that first fiber network over the top of your copper network. As you go from GPON to XGS-PON, you didn't always deploy a second fiber to the home. So this is what the standards bodies came up with. We're going to leverage different wavelengths that can run on that single mode fiber. And these are some of the first applications that are bringing multiple technologies together. But in my opinion, we're really just in the infancy of DWDM and the amount of bandwidth that we can move across single mode fiber. So the future, like 50 gig PON, that's a big number. But your next standard after this is actually looking like 200 gig PON. We've got a ways to go for that, but the numbers keep getting bigger and bigger because we have that superhighway that is single mode fiber.
Yeah, and that's fascinating because we actually just had a training with precision optical technologies, and that was one of the things that we talked about is most of the really exciting advances has been around the optics at the end of the fiber, right? Yeah. The active devices and their ability to transport, higher and higher data rates through the same fiber, enabling multiple wavelengths and higher data rates to, push more data through the same pipe that's been out there for, in some cases, decades. Yep. And that's the really exciting part, is seeing how the industry evolves. In the creativity and the ingenuity and innovation in the optical technology space. The fiber in between is really largely unchanged. Yep. Fiber splitters aren't super complicated or super sexy, but they're hugely important. But it's the real magic is in those active devices on the ends. So exciting stuff.
Yeah, absolutely. A lot of conversation. PON it's a very broad topic because there's so many different aspects that get put into it. You're in the optical domain, you're thinking about data rates, you've got all the different deployment considerations with that active OLT and ONT. But when you start kind of peeling things back, there's really a few core competencies or core points that you need to understand. This piece about the wavelengths, having a little bit of understanding about where each standard comes in terms of bandwidth, and then your outside plant architecture, and it gets very very easy to comprehend. But for a lot of people, when you lay it out on paper and you say, yeah, we're going to do this, we're going to take this single thing and divide it all these ways, if you don't understand some of these kind of core internetworkings, it seems a lot like black magic. But if I'm the guy behind the curtain, that curtain is a little in my opinion, pretty transparent. If you spend a little time, maybe listen to listen to a few more sessions like this, so it all comes together for most people pretty well.
Yeah, I appreciate your time, Greg. It's been really informative and enlightening to get behind the curtain of PON a little bit more. So I want to thank again Adtran putting together this training with us, again in partnership with the Penn Ohio chapter of the SCTE. Adtran bringing the world together, and it was great to get together with you today, Greg. Hopefully we'll do it again, and maybe next time we'll talk about troubleshooting and other things that could be considered in managing your passive optical networks.
Yep.
But awesome stuff. Thanks again. Appreciate the partnership, and we'll talk to you again soon.
Alrighty. Thank you very much. Appreciate the time and the logistics on all of this. It's a great series.